Welcome back to part 2 of simplifying non-variable radicals of higher degree. I'm going to pick up where I left off, and we're going to be taking a look in this part of the lesson about understanding when the radicand is negative. And again, just quickly, by radicand we mean the number under the square root sign or the nth root sign. In this case, if I did the 7th root of 45, the radicand would be 45. Okay, so we're going to try and make a quick observation here about what happens when we take a higher degree root of a negative, and specifically I'm going to work with the radicand of -1 because it's decently simple, and hopefully it's going to illustrate a property that you'll be able to sort of see and apply in problems where the radicand is a negative other than 1, but using a radicand of -1 should pretty much demonstrate our point here. So in this first problem here, it says the third root of -1, which means what number times itself 3 times is -1. Well, if I just did that on my calculator by hitting the math button, selecting number 4 from the menu for the third root, and getting -1 as the radicand, you'd see I would get -1. Okay, and so I'll put -1 here, and then, similarly, if I did the fourth root for getting the fourth root of -1, so doing 4 math 5 of -1, we see that it's in fact undefined because it's a non-real answer. Okay, so I'm just going to put a little undefined symbol here. And then if I went to the fifth root by doing 5 math 5 -1, I would get -1. And then if I did the sixth root by doing 6 math 5 of the radicand being -1, I would again get a non-real answer. So that's going to be undefined. And then if I did the seventh root, which would be 7 math 5 for picking the xth root, again, of -1, I in fact get -1. Well, I should see a pattern here where, if you notice, I am going to sort these answers into these little bins here. And you probably see the pattern happening that the next answer probably would have been the 8th root of -1 being over here as undefined. Okay, so what does this mean as we examine more closely? Well, if we notice, we're going to be able to generalize from this principle. If you have an even root of -1, or any negative for that matter, it's going to be undefined. But if you have an odd root of -1, the answer is -1. This just means that you need an odd number of factors of -1 to in fact get -1, but an even number of factors will never yield a negative. So from here we should be able to see that as long as we have the xth root of -1, it's equal to -1 for x is odd. But we're going to get that x root of -1 is undefined for x being even. Okay, so let's try and use that property when we make our factor trees, when we actually try and simplify using negative roots. We'll just keep that in mind and realize, well, if you have an even root of a negative, that there's no real answer for it. But an odd root of a negative just means that we're going to get a negative root value, and it's completely possible. So let's actually just move on to a couple examples here and see how that goes. Now, the one thing I want you to recall as I do some of these examples where I'm asked to please simplify with an exact, let's say it should say value, excuse me, it shouldn't say variable. Okay? I want to take you back a few slides into what we looked at in video 1. I'm not going to redo it, but I just want to refer to it. And that is, in fact, where we said we're going to throw out the biggest square method and do the 2 for 1 method when we were doing square roots. Well, the one thing I want you to realize is when we write square root of, say, 9, okay, there in fact is no number written right here. Well, that number that's not written is actually 2. And this should make sense because when we do square rooting, we're saying what two identical factors make 9. So you can generalize this where when we did square rooting, we actually did the 2 for 1 method. Well, as we now elaborate and do things like cube rooting, we're just going to use the 3 for 1 method. And for fifth rooting, we're going to use the 5 for 1 method. And for fourth rooting, we're going to use the 4 for 1 method, which just means we're going to make our factor trees like we always have, but instead of trying to identify pairs, we're going to identify groups that are equivalent to the index number. Okay? And this comes down to the fact that the property of the nth root of x to the n is equal to x. Okay? So it means if you are doing nth root and you have n factors, they will cancel each other and just give you x. We want to keep in mind that we want to apply this idea of being able to use negative roots for odd indices as well. Okay, so let's see what we have in this first problem. Okay, it says 5 times the cube root of 440. So I am going to make a factor tree. I'll multiply my answer by 5 when I'm done, because that's what it says in the problem. But I'm going to make my factor tree, and I'll start with 2's. I'm going to do 2 and 220. Then I'll do 2 and 110. I'll do 2 and 55. And then I'm going to do 5 and 11. And if you notice here, I tried to break my factor trees consistently using the smallest prime number available, then the next smallest prime number available. It's going to help me try and just stay a little more organized as I write. Well, when I'm doing the cube root, I need to find 3 factors that are identical. So if you notice here, instead of doing 2 for 1, I'm going to do 3 for 1. So I've got 3 factors of 2. So I pull the 2 outside the cube root. And then if you notice, I've got a remaining factor of 5 and 11. Well, because I don't have 3 of them, I won't be able to pull them outside the root. So they're going to stay inside the cube root. And I could just say that they're 55. And I've got to make sure that in my writing, I bring down this 5 as part of the problem. So it's 5 times 2 times the cube root of 55. So which just makes the answer 10 times the cube root of 55. I could check that answer by going to my calculator and saying that I've got 5 times cube root, by going to my math window, the cube root of, actually I would have rather, like I said, stay with the smaller prime numbers, okay, and realize that maybe 2 and 75 would have been more helpful. And then I'll get 3 and 25 and 5 and 5. Okay? So where I'm looking for fifth roots, there's a couple things going on here. Is one, that I've got a fifth root of -1. So that's just going to be pulled out to be -1, like I showed on the previous slide, because it's an odd index of a negative, which is totally possible. And then I'm going to look for groups of 5. So I've got 1, 2, 3, 4, 5. So the 5 for 1 method says I can pull those 5 factors of 2 out and make it 1, 2. And then On the inside, I'm still doing the fifth root of my remaining factors, which are 3, 5, and 5, which is going to be 75. Making my final answer negative 2 times the fifth root of 75. And again, you can check that on your calculator. So this next one looks like a monster, doesn't it? Well, we'll try and be patient with it. And maybe I'll just pause the video and do the factor tree to save you a little time in watching. But again, I'm going to try and break it down by 2's. And I'm going to use my calculator to assist me. So I'll take a second and it'll magically appear because I'll pause the video for a moment to do this work to save you a little time. So I just took a second to factor that with my calculator. It was a bit of a monster of a factor tree. If you just notice where it stopped here at 405, I just continued it up here where I was running out of space. Okay, so if it's the fourth root, I'm looking for groups of 4. So the fourth root of 103,680 will break down to this. Let's see. Well, I've got 4 4's here, 4 2's here. So I'll pull out that 2, change colors to help visualize this. Then I get another quartet of 2's. So it's another 2 that I pull out. And then if you notice, I've got another 4 for 1 opportunity with these 3's. And from there, if you notice, the only remaining factor I have is this 5 that stays inside the fourth root radical. So this, in fact, will make this answer 2 times 2 times 3, which is 12 times the fourth root of 5. Wow. Not overly hard, but just longer. You can't get intimidated when you see 103,680 because you're just going to keep breaking it down into smaller factors if you're patient. So what's this in a nutshell when we did these examples? Well, if you think when we did square roots, we did this method that we called 2 for 1. Well, again, for cube roots, you're just doing 3 for 1. And for fifth roots, you're doing 5 for 1. For fourth roots, you're doing 4 for 1. If you had seventh roots, you'd be doing 7 for 1. Now, we don't ask you to do many of those by hand because the numbers that we have to use tend to be so large to get 7 factors. If you're doing seventh root, even you saw when I was doing fourth root, some of these factor trees are large. But it really comes down to this principle again, that you're going to need to move to when you go into variable expressions with degrees of higher degree with radicals. And let me just write it again to be more clearly, okay? And it is in fact that if you have the nth root of x to the n, it will be equal to x, okay? So when you're doing the nth root, we want to be able to account for n factors. So if you have the 7th root, you'll look for 7 factors to pull out. If you have 5th root, you'll look for 5 factors to pull out of the radical. So as you do these, you'll start to make connections and it'll start to solidify. This is just sort of a writing method of organizational approach to help you just get the right answer. And again, you're just simplifying one value into another form, but they are in fact the same number. So feel free to watch this again. I hope it was a decent explanation for a video explanation, and I hope you enjoyed it.